We're here this morning at the excavation of the Worthington Diamond Mine. We're located just a short distance outside of southwest Arkansas's famous Crater of Diamonds State Park. This is a portion of one of 7 known diamondiferous intrusions outside the Crater of Diamonds. We've mined right up to our property line. As you can see, this fence indicates our property line. And we dug here because diamonds were found right across the property line, and we are finding diamonds here on this side. It's funny how volcanoes and diamondiferous intrusions don't respect a property line. Of course, there was no such thing when the volcano intruded, but anyhow, this is what we are excavating, and we have excavated in here in the past, and we keep it to where it drains so we don't dig too deep, because I don't want to pump water. It drains off through here. So I just wanted to show you the excavation. Now, it intruded all the way to here. I saved about a foot of the lamprite because I didn't want this clay to wash in and contaminate our sample. I just want to wash pure lamprite when we process, and I don't want a bunch of clay mixed in it. So I left about a foot of lamprite on the right side here, the east side. Now, this is what the ore body looks like. Now, we've dug down and taken that out, but you can see it's fractured along here, and this is a natural fracturing, and it went right in line with the edge. In other words, it's perpendicular to the edge, and so we have, it indicates a pretty steep side to this. In other words, the lamprite goes down sharply. It's not funnel shaped going this way. So anyhow, we have lamprite for a long way down. In fact, it's been drilled right by our property line, hundreds of feet thick. So more than I'll ever mine in my lifetime. I'm going to play with this for just a minute because I think this is kind of cool. So this is really rock solid, hard volcanic rock, but because it naturally fractured along here, we can break it up easily. Now, this has been out in the air for a while. When it isn't out in the air, it's a lot harder than this, but because it's fractured, we can dig it with a skid steer or excavator, and this will run through the plant real well. We have to have it crumble to release the diamonds that are inside the solid rock, this volcanic rock. This is diamondiferous lamprite, and it's a breccia because it has angular clasps in it. But anyway, pretty neat stuff. Now, I wanted you to pay attention to the fracture lines going this direction. This is north and south here. And I want to go around, play with it a little bit more. I want to go around and look at something up here on top because we're going to excavate this soon. Now look at this. This is going in line with the fracture, and this seems to be a seam of either barite or calcite. And look, it goes all the way from up here down, and there's another there, so it's filling with, you know, hot waters, hydrothermals kind of fill this. There's a root that has gone in that crack trying to get moisture. There used to be a forest here, and we cleared it so we could get to this lamprite that nobody had touched before. And we had all these trees on it showing the lid of the treasure chest had never been opened. This is kind of interesting too. This is a piece of Trinity clay. You can tell by the color. This is red Trinity clay. And what happened is there was a layer of this sediment, this red clay, a very hard Trinity clay. And there was earthquake faulting eons ago, and volcanic material burst through that layer of Trinity clay. Well, as the volcano busted through, it grabbed pieces of that clay and it incorporated it into this breccia. The good thing is, see, you need the volcanic rock to cool down quickly to retain the diamonds. And this acts like a big ice cube, because this was room temperature. When this molten lava hit it, Well, this helped cool down the iced tea quicker, if you think of that as an ice cube. So it cooled it down quicker and retained the diamonds. If it had stayed hot for a long time, the diamonds would have just burned up, turned to CO2 gas, because they're just carbon, and so they have to cool quickly to retain themselves. But our diamonds are somewhat resorbed because it wasn't a flash cooling. I want to get up here and show you. Now, see, we've been excavating here, and that's a pretty deep drop, and he's going to get all of this pretty soon. But before he does, I wanted to look at this and talk about this seam here. Mac brings me ore every morning. He comes with a skid steer and pokes in there and scoops it up and brings it to me at the rate of 10 half-ton loads an hour. So that makes 5 tons in an hour. So to explain this, we had a forest here with trees, and the stumps were removed. And then there was about 3 feet of clay on top of about a 1-inch layer of jaspers. These are like ocean cobbles, gravels, cobbles. I set these here just to demonstrate. That's about how thick the layer was. And we had the bulldozer take the clay off the top and the gravel off the top. When the volcanic intrusion came and brought diamonds to the surface from about 100 miles deep, at about the speed of Mach 2, it hit a shallow sea. Well, after everything settled and cooled, you know, the sea moved back in here, and there was tidal action, and it rolled these rocks around and smoothed them off. So these jaspers are rounded because of tidal action, wave action here in a shallow sea. So it deposited a layer of gravel on top of the lamprite, and I just brought these here. This is what the dozer had pushed off, and I brought them in just to show you that's about how much gravel we had. We didn't have a 2 or 3 foot thick layer of gravel, just a little bit. Well, now I showed you north and south is where the natural cracks in this go, and here east and west we've got a fracture in here. So there was original earthquake faulting that allowed the volcanic material to come up. So there was subsequent earthquake faulting in here too. I mean, you don't have just one crack and you're done. So as the crust of the earth was cooling back at that time, it cracked some more, and it looks like it left a crack in here. And I want to investigate that crack some, especially right here. It's interesting. So let me get my tools, and investigate this. So we'll sweep this away a little. So to me, this is a mud bubble, and we found mud bubbles in other places here. We looked at them in earlier videos, and they were more like dinner plate shape and size. They were rounded. This one is kind of oblong. Well, that just has to do with the crack. Now, it's kind of interesting. We've got a crack going this way, and we looked at that a minute ago. But we've got this mud bubble here, is what I think it is. And if you can see, there are fractures going this way, the natural fracturing going north and south. And then this is a crack going east and west, and it's filled with, you know, hydrothermal. Hot waters were bubbling up here and left minerals behind. Now the question is this mineral barite or is it calcite? And we'll do a little experiment here and find out. But we've got a couple of cracks going this way, and I'll just do a little sweeping. These are really thin, but you can tell this is a different material than the volcanic material. Let's just clean it up and take a look at it. I just like to investigate because pretty soon the skid steer will have this all dug up and we won't be able to look at it. But one thing I want to see if this material is the same as this material, or if it bubbled up something different. If we have barite over here and calcite there, or the other way around. just interesting. But now, on top of this too, the top foot or so of this laterite has a lot of purplish black rock, which is a limonite goethite. You can kind of see the purplish black in here. This is iron and manganese. That limonite goethite is an iron and manganese. And if this vein that is here is either calcite or barite, if down below it's a hybrid and maybe it opens up into a vug that the hydrothermals maybe made quartz crystals in there, those quartz crystals could be amethyst, which is purple quartz, because of this manganese and iron. Manganese and iron in hydrothermals, in the hot water, mixed in there, is what makes amethyst purple. So I'm interested in this because this could open up into a void down here that could have amethyst. I'd love to hit an amethyst vein. That'd be exciting. But right now, it looks like there's a cobble that's been caught up in this mud bubble. Now this mud bubble is now like cement. It is really hard. So I'm going to take a chisel and see. Okay, there's a jasper that came out of that. So we had a shallow sea here, and hot waters were boiling up, and some of the jasper from that shallow sea was caught up in those hot waters, and then it formed almost like a concrete around it. Okay, here's a jasper I didn't see that was down in there. So, oh, and there's more. So I think this was liquid just bubbling up, and it would grab the jaspers that was on this sea floor, and they got incorporated into this cement type. I'm thinking it's calcite, but we'll see in a minute. There's an experiment we can do with some muriatic acid. It'll only take a moment. So stick with me, we'll find out. There's another jasper in there, and it's got that calcite or whatever stuck to that jasper. So anyway, this is like concrete in here, and I would love for this to open up to a big amethyst vein. That's what I want. Here again, mixed with the hydrothermals, you've got this black, this purplish black, is your manganese and iron. See the manganese and iron in that? It's real purplish. Get a close look at this, but see in the morning sun, that's your goethite, limonite, manganese and iron that gives you the purple in amethyst. So I'll play with it just a little bit more. But I've always wanted to bust up one of these mud bubbles and see what it's like. And this one, oh look, a jasper came from deeper down in there. That's cool. Got more jaspers in there. So I'm just investigating, playing. So the mud bubble seems to be getting smaller, but there's still this crack, this fissure here. All right. Well, it seems like this material is about gone. The mud bubble was just here at the surface, and so down below it's just a narrow crack like there, but here at the top it just bubbled up. So anyway, we dug it up. But let's there's a jasper in this concretion, whatever that it feels like concrete anyway, the mud bubble. Here's another jasper and another jasper in there. No, that's just one. But anyhow, I'm going to pour a little acid on this and see if it bubbles, then it's calcite, and if it doesn't bubble, then it's barite. But we'll see what we've got. Here's that manganese and iron. So we'll try a little muriatic acid on this. No, it's not calcite. I'm not sure that it's barite either, but anyway, it's not calcite or it would have effervesced. But that's interesting because I really thought it would effervesce, but it doesn't. There's a jasper in that. So interesting. It's just a mud bubble, just mud bubbling up from the heat. Hot water is boiling beneath there. I'm going to check over here and see if this seam will bubble up or not. See if this is calcite. So we'll give this a try. No, it does not effervesce. Oh well, that's why you test it. You learn. But anyhow, been fun playing with this, and thanks for checking out what's going on at the Worthington Diamond Mine.